And welcome back once again to History of Mathematics. We are continuing our work through Stuart Hollingdale's book, Makers of Mathematics, and discussing Chapter 13, which is about D'Alembert and his contemporaries. Now, you'll remember that the author is choosing D'Alembert as a representative of the entire period 1750 to 1850, so all that work done between Euler and Gauss, who we will meet in the next chapter. And another thing to remember that we discussed in our last video is that this period sees a flurry of activity involving calculus and its applications, in particular differential equations. Now, last time we discussed differential equations applied to the area of population growth. So what we have in that situation is a scenario in the physical world that we can describe with a mathematical equation that involves a derivative. So the situation there was the rate of change in population with respect to time is proportional to the population at any given time. And here we're going to see another scenario where a real-world situation can be described by a differential equation. So let's switch to the document camera and look at that. Okay, so here we've got a statement of Newton's law of heating and cooling. And it says the rate of temperature change for an object is proportional to the difference between the temperature of the object and the temperature of the surrounding medium. So, change in temperature with respect to time is proportional to, in other words, is a constant multiple of the difference between the temperature of the object and the temperature of the surrounding medium. Now, I always have to think a little bit about the order here in which I do this. So, if I take a very warm object and put it into a cold surrounding medium, let's say I take a hot cup of coffee and I put it in the refrigerator, we would expect the temperature to decrease. The temperature of the coffee should decrease. So I think I need the order to be like this. So M stands for the temperature of the surrounding medium. T is the temperature of the object. Oh, and also little t, that is time. So little t is time, big T is the object temperature, and capital M was the medium temperature, the temperature of the surroundings. Okay, and I think this works because if the temperature of the object is bigger than the temperature of the medium, this quantity would be negative, meaning the object is going to cool down. If I take something that's cold and I put it into a surrounding medium that is warm, we would expect the object to start to heat up. Let's say I took something from the refrigerator and put it into the oven. Well, we would expect the rate of change to be positive now, and there the medium temperature would be greater than the temperature of the object, so this would be positive, and we would see that increase in temperature. Okay, so this is another equation, another differential equation that can be solved by the separation of variables. Okay, now we have to make a careful distinction between capital T and lowercase t because they stand for different quantities. But the strategy is the same. I get everything that has a capital T to one side and everything that doesn't have a capital T over to the other side. And now integrate both sides, so this is the stage where we separate. Now we're integrating. Okay, so on the left-hand side, we're integrating with respect to capital T. On the right-hand side, we're integrating with respect to lowercase t. Right-hand side is easier. That is a constant. Okay. On the left-hand side, I would get that. Okay, one sec. I think I actually need a negative out here. What I would do is make a u substitution, let u equal m minus t. So du would be negative dt. So I need that negative out there from the substitution. Okay. Now, what I want to do is I want to solve this for capital T. Okay, I want to solve that for capital T. So I'm going to use exponentials, but before I can do that, I want to get that negative out of the way. Okay, notice I kept the plus c a plus c. That's just an arbitrary constant, so negative of an arbitrary constant is still an arbitrary constant. So don't worry too much about that. Now we'll take the exponential of both sides. On the left side, the exponential and the log undo each other. Okay, using rules for exponents there. Now remember what I want. I want to solve for t. So I'm going to get rid of the m by subtracting m from both sides. But that doesn't get me t, it gets me negative t. So I'm actually going to end up with this. Okay. I'm going to end up with this. So A is dependent on the initial temperature of the object, but it's not exactly equal to the initial temperature of the object. Okay, we'll see that when we look at a concrete example in just one sec. Okay, but this is the scenario here. Now think about this function. Okay, there's your constant m right there, and that was the medium temperature, the temperature of the surroundings. Notice you've got a negative up here as part of the exponent. Okay, so when t gets large, this part gets really small. And in fact, that's saying that as time goes by, the temperature of the object gets closer to the temperature of the surroundings, which is exactly what we would expect. Okay, so let's look at a concrete example of how this works. Okay, so here's the concrete example I want to work on with you. So let's imagine we have a piece of metal, and we heat that metal up in a furnace to 100 degrees. And we place that heated metal into a tank of water that is held at 40 degrees. Okay, now you've seen scenarios like this, I'm sure, in videos and stuff like that, but if you want to shape a piece of metal, you usually have to heat it up so that it's pliable. Okay, and I'm sure you've seen them, take that heated metal and hammer it into the shape they want, and then when they do that, they put it in some water, and you get that sizzling sound, that tss sound, right? So let's imagine that tank of water is heated to 40 degrees. Now, after 2 minutes, the metal is 80 degrees. Now the question we want to ask is, when will the metal be 45 degrees? So the strategy is going to be the same thing, same basic principle that we saw in the previous video with population growth. We're going to write capital T, the temperature, as a function of time. Now, the way that we are going to get capital T as a function of little t is we're going to use that differential equation. And then the second stage is going to be we're going to solve an algebraic equation that'll tell us when the metal will be 45 degrees, and that'll actually answer the question. But we won't be able to get to that part unless we can express temperature as a function of time. Okay, so Newton's law of heating and cooling says that the rate of change in temperature with respect to time is proportional to the difference between the temperature of the surroundings, which we know is 40 degrees, and the temperature of the object, which is an unknown function. Okay. Now, we saw just a few minutes ago that this differential equation can be solved with separation of variables. All right, so let's assume I did that, and I did the work there. I'm going to get this. Okay. If you look back, you'll remember that we had the temperature of the medium right here. I said A depends on the initial temperature of the object, but is not equal to the initial temperature of the object. So let me show you what's happening here. Okay. I know that when little t equals 0, when little t equals 0, this is supposed to be 100 degrees. Capital T equals 100. Okay? So, that tells me this. Capital T is 100. Oops, let me put in a 0 there. We said little t was equal to 0, right? Let me just do that. It's e to the 0, right? Now, of course, e to the 0 is 1. So this is 40 minus a, so then we can solve for a. A equals negative 60. All right? So that tells me that the temperature of this piece of metal is going to be given by this equation, 40 plus, right, because that negative, two negatives, 60 e to the negative kt. All right, so I used the initial condition to find that value right there. All right, now I still don't know k, so I'm going to use the information that they gave me here. After 2 minutes, the temperature of the object is 80 degrees. It said that right here. After 2 minutes, the metal is 80 degrees. So to find K, we're going to solve this equation right here. So 80 degrees equals 40 plus 60 e to the negative 2k. I plugged in a 2 for the t right there. All right. So I'm going to solve for k using logs. Subtract 40 from both sides. You'll have a 40 on the left. Divide by 60. Okay, so that's actually going to simplify to 2/3 equals e to the negative 2k. And when I use logs to solve, I get this. And we'll use a calculator to do the calculating. Let's see, relatively little glare there. So what I'm going to do is I'll do ln 2 over 3, whoops, ln 2 over 3, divide that by 2, whoops, negative 2, so approximately 0.2. So that's our k value. And that lets us get the function for temperature, 40 plus 60 e to the negative 0.2 t. So this expression right here will tell me the temperature of the metal at any time t. A few things to notice. If you plug in t equals 0, this is a 1, and you have 40 plus 60. And the statement of the problem said that the metal starts out at 100 degrees. Okay, so it checks out there. I bet if we plug in t equals 2 and did the computation, it would work out to be 80 degrees. Because that also matches, and that's basically how we got the value of k. The value of k that we chose, the value of k that we solved for is one that will make this equation into a true statement. Okay? Now, the last step was to find out when the metal will be 45 degrees. So the last step is to solve this equation for little t. It's actually going to be a very similar process to solving this equation right here. We would subtract 40 from both sides. That leaves me with a 5 over here. Divide by the 60. So we'd end up with this, e to the negative 0.2 t equals now 5 over 60, that's 1/12. And then we'll use logs. ln 1/12 divided by negative 0.2. Okay, once again calculating with my calculator. Divide that by negative 0.2. So that'll be happening in approximately 12.4 minutes. Okay. Now remember, the temperature of the metal will approach 40 degrees the longer it is in this water. If you want to hit 45 degrees, you got to wait 12.4 minutes. If you wait longer, the temperature of the metal will be closer to that 40 degrees that the water is. Okay, so that is another class of problems that we can gain insight into using differential equations. And as I mentioned in the previous video, differential equations is a massive subfield in mathematics. You could take several college courses about solving differential equations. So we're just giving you a kind of tip of the iceberg to give you a flavor of what people were doing in this period, 1750 to 1850. Now, in our next video, we're going to move on to chapter 14, I think. Yep, chapter 14 of Stuart Hollingdale's book, Makers of Mathematics. So we'll put a link to that video right down there. And that chapter is going to be about Carl Friedrich Gauss, who is basically a titan of mathematics. If you ask most professional mathematicians who the greatest mathematician in history is, they'll probably say Gauss. Okay, the big three are Gauss, Newton, Archimedes. Remember him from back in the beginning of the book. Euler is usually ranked right under Archimedes, and the folks that we're talking about in this chapter are usually ranked right under Euler. Folks like Lagrange, Legendre, Laplace, D'Alembert, that whole crew. So check that next video about Gauss, and we'll see you later.